Stellar black hole. Although technically not a star anymore, this is the final collapse of a gigantic star. With an event horizon often only 20 to 40 miles in diameter, they are terrifyingly small. Take Cygnus X1, for instance. It would barely fit into the Greater London area or the Ruhr Valley. Yet their gravity is absolute. Not even light can escape. They are the dark points on our canvas around which everything revolves. When they feed on matter from a neighboring star, they form an ultra-hot accretion disk that shines brighter than 1,000 suns. Neutron star, a bit larger but no less extreme. Neutron stars are born when the core of a massive star collapses under its own gravity, crushing protons and electrons into neutrons. With a diameter of only about 12 meters, they would fit inside a city like Munich, yet they weigh more than our entire sun. Just 1 teaspoon of their matter weighs about 1 billion tons. They are unfathomably hot. Spinning spheres that often blast radio waves across the cosmos like a cosmic lighthouse. Magnetar. A magnet is a rare nightmarish variant of the neutron star. It has roughly the same tiny size but possesses the strongest magnetic field in the known universe. A quadrillion times stronger than Earth's. If a magnetar were to fly past Earth at the distance of the moon, its magnetic force alone would wipe every credit card on the planet and likely kill every living thing by distorting the electron clouds of our atoms. They are prone to star quakes that unleash gigantic amounts of gamma radiation. White dwarf. A white dwarf is what remains of stars like our sun, the naked glowing core. Our neighbor Sirius B is a perfect example. It's about the size of Earth, but packs the mass of a sun. It is essentially the diamond of the sky. Extremely dense and hot, but without active fusion, it slowly cools down over billions of years until it theoretically becomes an invisible black dwarf. In binary systems, it can turn into a vampire, sucking matter from a companion star until it finally explodes in a supernova. Brown dwarf, the failed star. Systems like Lumen 16 bridge the gap between gas giants and true stars. With a radius about the size of Jupiter, a brown dwarf is much more massive and dense. It lacked just a tiny bit of mass to ignite hydrogen fusion. Instead, it glows a dull red, burning deuterium, before slowly fading over eons. It's warm rather than hot. Theoretically, even host clouds and weather phenomena in its atmosphere. Red dwarf M-type, the most common type of star in space, making up about 75% of the total population. Our nearest neighbor, Proxima Centauri, is one of them. They are small, 10 to 50% of the sun, cool and extremely efficient. A red dwarf burns its fuel so that it can live for trillions of years longer than the universe will likely continue to produce stars. They are often very volatile, blasting massive radiation storms, also known as flares, into space, making life on their planets a real challenge. Orange dwarf K-type, the often overlooked middle child between red dwarfs and the sun. Stars like Alpha Centauri b are slightly smaller and cooler than our sun, with approximately 60 to 90% of solar size. But they live significantly longer, up to 30 billion years. Many astrobiologists consider them the perfect candidates for finding alien life, because they are more stable than red dwarfs, and longer-lived than yellow dwarfs. They shine with a gentle orange light. Yellow dwarf G-type. Our sun is one of them. A stable star with a diameter of 865,000 miles. It fuses hydrogen into helium and is currently in its prime. Yellow dwarfs are white, yellow, and live for about 10 to 12 billion years before they bloat up. They are the standard by which we measure all other stars, large enough to keep us warm but small enough not to grill us immediately. White main sequence star, a type. When we see the brightest star in the night sky, it's usually this type, like Sirius A. They are about 1.7 to 2.5 times the size of the sun, but much hotter and more luminous. Their light is pure white, often with a slight blue tint. Because they burn hotter, they live shorter lives than our sun, only about 1 billion years. They are the local celebrities of our stellar neighborhood. Wolf-Rayet star, an absolute monster of energy, though not necessarily of size. Wolf-Rayet stars, like the heavyweight champion Tiryur R136A1, are extremely massive stars right before they explode. They are so hot and radiate so intensely that they literally blow their outer layers into space. Although they might only be about 30 times the size of the sun, they shine millions of times brighter. They are often surrounded by beautiful glowing nebula, made of their own material, a spectacular deathbed. Before we enter the realm of the giants, I just want to say a huge thank you for watching this far. If you are enjoying this cosmic journey, I would really appreciate it if you hit the like button and subscribe to the channel for more fascinating content. It really helps me out. Now, enjoy the rest of the video as things get truly massive. Red Giant, the retirement age of normal stars. When our sun runs out of fuel, it will turn into something like Aldebaran. Red giants are huge, bloated gas balloons with 10 to 100 times the radius of the sun. Their surface is relatively cool, hence the red color, but their sheer size makes them extremely bright. They often swallow their own inner planets. Blue supergiant. While red giants are bloated seniors, blue supergiants are young, brutal titans. They form from extremely massive stars, with about 70 to 100 times the solar radius. Stars like Riel and Orion are smaller than their red counterparts, but much hotter and denser. They burn through their fuel at a breakneck pace and end in spectacular supernovae after just a few million years. Riel is a beacon visible across gigantic distances, red supergiant. We are reaching dimensions our brains can barely process. When a blue supergiant cools and expands, it becomes a red supergiant, like the famous Betelgeuse. With 1,000 times the solar radius, Betelgeuse would reach all the way to Jupiter. These stars are giant vacuum chambers. Their outer layers are as thin as a laboratory vacuum on Earth, yet glowing hot. They often pulsate as if they were breathing, teetering on the brink of collapse. Red hypergiant, the largest known stars in the universe. They exist at the absolute limit of what physics allows. Giants like UI Scuti or Stephenson 2-18 are over 1,700 to 2,100 times the radius of the sun. They are so huge that light takes hours to cross them. They are extremely unstable, losing the mass of several Earths every year through stellar winds. If you place Stephenson 2-18, where the sun is, its surface would reach almost a Saturn. A commercial airplane would need 1,200 years to fly around it once. Thorne-Jitkoff object, although currently hypothetical with only potential candidates like HWV 2112, observed, this is a true Frankenstein star. The scenario, a red supergiant swallows a neutron star. For example, in a tight binary system, the neutron star sinks to the center and replaces the core. From the outside, it looks like a red supergiant, like Betelgeuse. But the chemical composition is completely bizarre. A star that has a dead star in its belly and is kept alive by its exotic and energy, quasi-star. This hypothetical monster from the primordial universe is the king of monsters. Before metals existed, gas clouds could become so massive that their core collapsed directly into a black hole without destroying the star. The star isn't powered by fusion, but by the massive energy released as the black hole feeds on the interstellar layers. With 7,000 times the size of the sun, it would be as large as our entire solar system. It lives only briefly until the black hole has devoured everything, leaving behind a supermassive black hole at the center of a young galaxy. Supermassive black hole. A supermassive black hole is the largest object that can form from stellar matter. Ton 618 is a black hole with 66 billion solar masses. Its event horizon has a diameter of nearly 248 billion miles. That is so large that a beam of light would need weeks to cross it. As a quasar, it shines brighter than all the stars in our Milky Way combined. This is where all imagination of size ends.